Ready to go? Okay. Well, thanks very much for the invitation to come and speak here. I spent a lot of time in Scotland, but very little in Glasgow, so it's nice to finally spend some time here and not just travel through on my way up to the Highlands. This is a fairly general talk. I'm keeping it light-hearted as much as possible, given that it's nearly Christmas. But yeah, we'll have a look at mass extinctions. Are we all doomed? Can I use that one? So what about that? I can't come to Scotland and not acknowledge this. The best game, as an England supporter, not really, best game I've seen in decades. So fantastic, well done. I look forward to Scotland knocking Brazil out of the World Cup. So, what we're going to talk about today, what is extinction? Which many of you might know what an extinction is. What is a mass extinction? Maybe less well known. How do we study extinction? So as the introduction said, I've worked on extinctions for too long now, 25 years. So I'll explain how I go about doing my research. We'll look at the big 5 extinctions through time. We'll have a look at a case study of the day the Earth nearly died, which is the End Permian Mass Extinction. What happens after an extinction? Why are we here? And then finally, some rather tongue-in-cheek, a little bit light-hearted look at today. Is today like the past? Are we indeed doomed? At the end, questions, please do ask. As I tell my students, I teach all sorts at Hull because we're a very small university. There's only 3 geologists. I have to teach human geography, amongst other things. But as I tell my students, this is one of the few topics that I actually know something about. So if you've got questions, I'm more than happy to take those at the end. So first things first, I do lots of stuff with the media. I talk to journalists quite often. When the pandemic came along, the previous one, not the new one, about flu, which seems quite scary. Hopefully I didn't catch that on the train. It was very busy. When the COVID pandemic came along, I got lots of questions about extinctions and viruses. So we can get this out of the way really quickly. Viruses do not cause mass extinctions. I was genuinely asked this, which was quite a shock to me. A virus has a host species. It tends to have one species that it's hosted by. Can of course jump from species to species, but it's really not in the interests of a virus to wipe out its host species. So no, viruses do not cause mass extinctions. We can move on from that and forget that straight away. Now, Darwin's survival of the fittest. You all know the theory here. So since most offspring do not survive the harsh realities of the natural world, it's a struggle to survive. Organisms must struggle to survive. Only those that survive long enough to reproduce are able to pass on their characteristics to their offspring. In time, characteristics that allow organisms to survive and reproduce become more common. And organisms that don't survive and reproduce will disappear. And this is how the population evolves. So, fairly straightforward theory. However, sometimes something interferes in that and extinction happens. Now this is a pile of passenger pigeons, which were once the most abundant birds in the skies over North America. And you can see here a great big hunting party has hunted many, many thousands in that pile probably to death. Here we have a lithograph showing what the skies were like. There are lots of anecdotal reports of the skies went black. There was, an eclipse caused by these birds. They were that numerous. However, in 1914, the last surviving passenger pigeon died in captivity in Texas. That's an extinction. In this case, a human-induced extinction. It was literally hunted to death. So that's extinction of a species. And over the past few decades, we've been aware of several species going extinct or becoming extinct. And we'll have a look at that a little bit later. But what is a mass extinction? It might surprise you that there is no formal definition in the literature of what a mass extinction is. There are several different definitions. This is the one that I like the most because it's the most straightforward, really. This is by Jack Sepkoski, who was one of the founding fathers, really, of extinction studies back in the 1970s, based in Chicago. This was his final paper. He died shortly after this was published. His definition was a mass extinction is a substantial increase in the amount of extinction suffered by more than one geographically widespread higher taxon during a relatively short interval of geologic time. Now, if you think about it, that's very subjective. What is a short interval of geologic time? Are we talking 10,000 years? 10 million years? If you work on Archean stuff, 10 million years is a pretty short interval of time, isn't it? But there are a few key things in here that we need to take from this. A higher taxon. So this is Carl Linnaeus. Of course, this is Linnaean classification and taxonomy, which hasn't really changed since he published this nearly 300 years ago. A few revisions to this. This example is the species, the moss rose, which of course fits within a genus, in this case the Rosa, within a family, the Rosaceae, within an order, the Rosales. The class is the dicots, and they are in the Angiosperm phylum, which is the flowering plants, and of course the kingdom at the top there is the plants. They're in the plant kingdom. So we have this very familiar hierarchy in which all life on Earth is classified within. The higher taxons there are the things at the top of that hierarchy, are orders, classes, phylums, and kingdoms. We can do a little analogy. So a silly analogy here, I'm going to use motor cars as my taxon here. So within the family Motorcaridae, we obviously have lots of different manufacturers, our genera. In this case, I've chosen the Forder. We know there are lots of different species belonging to the Forder. The Sierra, the Fiesta, the Tea, the Focus, the Capri, and the Transit, they're all extant, alive at our time 1. Let's move across our extinction boundary. We've wiped out 3 of our species, and our extant species now are the Fiesta, the Focus, and the Transit. We've lost the Sierra, the Model T, and the Capri. Very sad. But our genus is still alive and kicking, and our family is most definitely alive. So the message here is that you have to kill a lot of species before you can wipe out a genus and very much a family. And throughout geological time and throughout the evolution of the motor car, we have radiations to fill those gaps. So in this time between 1 and 2, Fords have radiated. We've now got the S-Max and the car and the 350. So actually, between time 1 and 2, although we've had 50% species loss, we've actually had 0 reduction in standing diversity. So let's move on to some of the databases that were created early on in the days of extinction studies. This is Jack Sapkowski on the left, who I mentioned earlier, and his student Dave Raup on the right. They were really extinction pioneers in the late 1970s, the early 1980s at the University of Chicago. This was a classic seminal piece of work that they put together in 1982, I think it was. And this is their first estimate of the number of genera, marine genera, through time based on a database, very early days for computers and databases here, of 30,000 fossil marine genera, going back to the Cambrian explosion there. So we have the Cambrian explosion of life on the left, working through geological time, the past 540 million years, up to the present day. Obviously, some of these things, like the tertiary, is no longer. That shows the age of the figure. But what you can take from this is, of course, diversity, marine generic diversity has increased greatly through geological time. Now, the real reason for that is that we simply have less fossil record. The further back in time we've got, that rock's either been subducted, that fossil record's been destroyed, or people just haven't worked on it. So there is clearly less Cambrian rock than there is modern sediment and rock. So that's the explanation for that general trend towards higher diversity through time. But the key thing on here is that we have 5 big thunderbolts here, where Sapkowski or Raup and Sapkowski recognised clearly that there were 5 periods in the geological record in which diversity crashed, really, really suddenly. So we've got these very, very abrupt declines in diversity, and they called these the Big 5 mass extinctions. In terms of a Premier League table for these mass extinctions, the End Permian is on top. So that's the one that we'll look at as our case study in a little while. I should revise that, 252 million years, wiped out about 96% of marine species. Then we've got 4 other events, the Big 5, of varying magnitude, but round about 75, 70 and 60% magnitude. Depending who you talk to, that figure varies, and I'll come on to some of the numbers in a little while. But clearly, these Big 5 events were major events. If you're wiping out 60%, 70% of species, you're also wiping out large numbers of genera and families as well. These are not just minor events in the history of life on Earth. I'll talk a little bit later about the Anthropocene, still in inverted commas, as the International Commission on Stratigraphy did not ratify it, which you may well be aware of. That was back in March of last year, so 10, 20 years of debate on whether the Anthropocene should be formalised, and now it hasn't. So we'll come back to that towards the end of the talk tonight. Currently, though, we have 0% extinctions in the Anthropocene. Doesn't mean we have none, but we have 0 if we round it up or down. Another way of thinking about geological time, which you may well have seen, is this spiral of geological time. But one thing I wanted to add to this are some lesser calamities. So my academic grandfather, if you like, was Tony Hallam, who was my PhD supervisor, and this was his term. He wrote a short little book about 20 years ago called Mass Extinctions and Lesser Calamities. A nice, easy introduction into the subject. So our lesser calamities on here are those yellow thunderbolts, and the big 5 are the big red splodges. One thing that's really obvious from this is that nothing much has happened in terms of extinctions on Earth since that one at the end of the Cretaceous, which is a very unique event. We have large igneous province eruptions in the Deccan Tract in India, but of course we also have the famous meteorite impact at Chicxulub in Mexico. I'll come back to that in a little while. But if you think, what we're going to talk about a little bit later is the present day, the modern and our future, we might be looking at this thinking, well, what was going on there and what hasn't really gone on since? We'll come back to the reasons for that in a bit when we talk about the Anthropocene. Another way of depicting that, don't really need to dwell on this slide, but this is essentially a revised version. This is a much more recent version. I've nicked it off Wikipedia, but this summarises that Raup and Sapkowski data quite nicely, just in a much more refined way. The databases are getting ever and ever better. We have something called the Paleobiology database, which is an extraordinary collection of marine and terrestrial plant and animal data, and that allows people to build diversity curves like this. It's been refined, but the point here is that however much you refine it, those big 5 extinction events still stand out. They're not artifacts of database quality. Excuse me. So how do we study a mass extinction? What do I do when I'm not teaching, which is about 5 minutes a week that I'm not teaching? We need some prerequisites. We need good dating. So we need to be able to correlate sections, geological sections, in wide areas. It's no point just looking at, let's say, Dobslin near Moffat, where the Ordovician-Silurian boundary stratotype is, and I've worked there several times. I could write a paper on Dobslin. I have written a paper on Dobslin. But if we don't compare that to data from other parts of the world, we can't really say much about extinction dynamics. So we achieve our dating through things like biostratigraphy, conodonts and ammonoids, and chemostratigraphy, particularly through carbon isotopes. So these are effectively, I'm sure many of you are familiar with carbon isotopes. They're like a chemical clock or a barcode, a wiggle. So we can match wiggles, shift in the carbon isotope curves, negative and positive, across many different areas of the world. Theoretically, they should be globally synchronous, those shifts. Then we need to look at timing. So it's obviously important to know when things became extinct and whether extinctions were sudden or gradual. If we see a lot of things disappearing within, a short interval of geologic time, as Sapkowski would call it, then we might be looking at a very sudden extinction driver, maybe something extraterrestrial like a meteorite impact. If we see extinctions dragged out over millions of years, that's a much less likely extinction cause. We're much more likely to be looking at something earthbound and a slow, gradual change. So we need to look at fossils and establish our fossil record in multiple places to be able to understand that. Then, when we've done that, we need to try and understand the causes of extinctions. So we study the same rocks that provide us with our fossil record to identify the killer. And we apply a whole load of different techniques to the rocks. Most of my work is geochemical, so looking for geochemical evidence, trace metals, things like that, for cooling or warming or marine anoxia when the oceans get starved of oxygen. We might be looking for evidence of volcanism, so again, trace metals, mercury, things like that are very good indicators of volcanism. We might be looking for evidence of bolide impact, so the obvious one is meteorite impact craters, but there are other indicators like shocked quartz grains and things like that that we can use to infer there was an impact. And the timing of this is absolutely crucial, so we need to know whether those things, let's say warming and anoxia, potent extinction mechanism, happening today, did they happen at the same time as the extinction? And if we can establish that temporal link, we can then start to establish a causal link. Ooh. So quick rattle through 4 of the big 5 before we get onto our case study. Just a slide on each, because otherwise I'll be here all night, and so will you. I don't know what the buzzing is. The Ordovician Silurian, this is the first of the big 5, or the earliest of the big 5, around about 442-ish, 43 million years ago. You can see this extinction in the graptolites at Dobbs Lynn. If any of you have been to Dobbs Lynn, it's a lovely section. It is a triple SI, so you can't collect there unless you have permission, which I did. But you can literally go and look at the record of this extinction at Dobbs Lynn. This extinction, marine only, so we haven't got terrestrial stuff at this stage. We've got the first plants starting to appear on land, but this mainly affects the conodonts, graptolites, trilobites, and brachiopods. Now, there's a lot of debate in the literature, which I won't go into on this extinction, but it's clearly two-pulsed. The first pulse is supposedly caused by cooling. The second pulse, some argue, is also caused by cooling. Some argue is caused by warming. So we've got the breakup of the Paleozoic ice sheet, the Gondwanan ice sheet at this time. So clearly, there's some climate change at play in this extinction event. Now, I have written a paper that this figure comes from. You've got actually it's not this paper, it's another one. It's a 2020 paper that suggests both of these extinction steps are caused by warming, which was quite controversial. I'll come back to that, and if you're interested, I'll show you some literature which you can get hold of for free. Late Devonian, again, widespread black shales associated with this event, much like the Ordovician Silurian event. I've had to put this on its side because if I put the sea level curve vertically, it doesn't really fit on the slide. But what you've got here is transgression going down. This is a sea level curve here from the early Devonian to the late Devonian. We have a series of marine transgressions, so deepening events, most of which are associated with black shales and marine anoxia, so oxygen starvation in the ocean. Each of those, they seem to be sort of disparate events, but they culminate in the Upper Kelvasser, or the Phanerozoic extinction here, which is the peak of sea level rise. So here we've got a clear case of sea level rise, anoxic events, probably linked to warming, although some argue not, resulting in this sort of cumulative extinction losses through the Devonian. This is what I did my PhD on with Paul Wignall more than 20 years ago now, which is rather scary. Triassic-Jurassic extinction event, one that I haven't really worked on, so this is just based on the literature. It affects all sorts of land and marine communities. It's devastating for reef communities in the oceans, but it's also rather devastating for various reptiles and amphibian groups. And it's actually after this that the dinosaurs have obviously got going by this time. But it's some of the non-dinosaurian reptiles and amphibians that get wiped out here, which really creates an eco-space for the actual dinosaurs that feature in Jurassic Park and then later into the Cretaceous to fill. Speaking of the Cretaceous, this is one of the best bits of scientific sleuthery I think has ever been done. So this is Luis Alvarez, who along with Walt, his dad, I think, published the famous paper in Science in 1980, suggesting that the end Cretaceous extinction was caused by a meteorite impact. Nobody had found a meteorite impact crater at this stage, but they recognised that the boundary beds were enriched in this metal called iridium, which is very, very rare on Earth and really only comes from impacts from outer space. So I thought that was, well, I was only 1 at the time, so I didn't think at the time that this was an amazing piece of work. But looking back now, as a scientist, I think that is a brilliant piece of sleuthery, and Luis Alvarez won the Nobel Prize for that piece of work. Later, the impact crater itself was discovered, so this confirmed, about 7 years later, after the publication of this paper, that they were right all along. It's a 180-kilometre diameter crater, which was probably caused by a 10-kilometre asteroid, that's now buried in it's the Chicxulub crater on the Yucatan Peninsula in Mexico. Part of it's on land and is now covered, and part of it's in the sea there, in the Gulf of Mexico, or Gulf of America, as Donald would like us to call it. The effects of this: wildfires, tsunamis, nuclear winter, mass death. Now, it's an incredibly hotly contested extinction mechanism. There are many out there that think that meteorite impact was nothing to do with this event, and it was all driven by volcanic eruptions. For that reason, it's a community, most of the scientific communities that I work with, I get on really well with. The extinction people are generally a good crowd. The people who work on this one are not, so I've avoided them like the plague. So I mentioned some papers. If you're interested in wider reading, especially if you're students that might be doing this stuff at university, there are lots of papers that I published. They're open access, so you can look me up on Google Scholar. There will be links to papers on each of the extinction events. Other authors are available. So there's this recent paper. This is based on the Dobbs-Lynn section published in Geology on the Ordovician extinction. That was the one I mentioned was quite controversial, suggesting that warming was responsible for both pulses. Paper here on the Late Devonian. We have some summaries of the End Triassic and Early Jurassic extinctions, and some more sort of review type papers that summarise all extinctions in the rock record. So loads of stuff, almost all open access, so you don't need to be a member of any society, although you obviously have access to the Lyell collection, but these are all freely available to anybody. So we'll get on to our main event in a moment, extinction metrics and severity. Boring slide, but it tells us a lot. So here we have a summary of different people's interpretations and statistical bendings of different extinction events. You can do anything with statistics. You can make whatever agenda you want. So there are 4 different summaries here based on different people's work, showing the ranking from 1 to 11 for different extinction events. One thing that's abundantly clear, whoever you are and whichever statistical methods you apply, the End Permian Mass Extinction comes out on top in terms of the extinction severity. This is percent marine genera extinct from various people's work, and we're looking at 58, 57, even 83 in one assessment percent of marine genera. So this is clearly the most devastating episode in the history of life on Earth. This is a different ranking. This is the Ecological Severity ranking from George McGee, I think it is. Yes, it is. So actually looking at how devastating these events were to communities. So slightly different to just looking at raw numbers. Even then, the End Permian event comes out on top, which makes it an ideal candidate for our case study. So we'll get on to the End Permian Mass Extinction, which was about 252 million years ago, colloquially known as the Great Dying, out of the frying pan into the fire. This was a time when Earth was hot, as this slide suggests. This, however, really, really annoys me, and that's me trying not to swear, which I've done, which is brilliant. This is the Discovery Channel DVD, which for young people is a thing that we used to have. It's the box, and it has this sodding meteorite impact on the front of it. There is no evidence for meteorite impact anywhere on Earth associated with the End Permian Mass Extinction. And it annoys me because the End Cretaceous is obviously very famous, the death of the non-avian dinosaurs. I go into schools and kids go, oh, meteorite impact. I go, no, it isn't. And it's stuff like this that perpetuates that idea. So anyway, that's my anger out of the way for the rest of the evening. This is the End Permian world. So paleogeographic reconstruction, this one based on Chris Scottese's work. He does this thing called the PaleoMap project. Lots of complicated data goes into making these. So magnetic susceptibility and PaleoMag and things like that, reconstructing the positions of the plates. So this is the End Permian world, clearly a very different place to where we are today. It's said that you would have been able to walk from the south to the North Pole without getting your feet wet. Almost, not quite, but nearly. So clearly very different to today. This is the time of Pangaea. So we have this world supercontinent where most of the plates are together as one. We then have the Panthalassan Ocean, or Panthalassa, all-world ocean there, and the Tethys in here, and then a few other important continents, North and South China in particular, where we have a lot of data from there out in the Tethys Ocean. So a very different world to today's, and of course that's going to affect the way that the world works in terms of particularly ocean circulation, but also wind and other circulation patterns. So I say to people who are thinking of becoming geologists, so my students, school children, etc., become a geologist because, as I'm sure you all appreciate, you go on your field trips, you see the world, and not as a tourist. You go and work with local people, and you see some absolutely amazing things. I've been so fortunate over the past 30 years or so to go to loads of fascinating places to do geology, so it's fabulous. This is Bolzano in the Italian Dolomites. This is me, that's me in the green t-shirt there, in a much thinner iteration. That's filming for Hungarian TV in the Buck Mountains on the Permian Triassic Extinction section. Lots of great records from Tibet. Done several field seasons there, including, as well as places like Spitsbergen. So my most recent work actually has been up in the Arctic, in Spitsbergen and Arctic Canada and Siberia. No more, sadly, or not for a long time. Japan has really great records from Panthalassa. So these are accreted terrains that show us really rare slivers of the deep ocean, which are really important to our understanding. Turkey, that was nice, that was hot, sunny. Ellesmere Island up in Arctic Canada, again some really important records that we're getting there from the northwest margin of Pangaea. Greenland, another northwest Pangaean record. And finally, weird places. Like, who would go to Idaho? It's famous for its potatoes, and that's about it. So geology really does take you everywhere, to places that you wouldn't ever think of going. And what do we know from visiting all these places? So this is a summary not of my work, but of the body of work that has been put together on the Permian Triassic Extinction. Our victims on land, this is pre-dinosaur, but our large herbivorous Permian reptiles are the pariasaurs, or the cheek lizards. They all disappear. The nasty predators, these are the gorgonopsids, sort of the size of a big pig, nasty sharp teeth. These are therapsids, so they're the top Permian predators on land. They all disappear. The gymnosperms, the naked seeds, these plants that formed the coals, things like Glossopteris, which is named after the town of Glossop in Derbyshire. This forms most of our coals in the UK, the Carboniferous coals. This dies out during this Permian extinction event. And most notably, perhaps on land, this is the only extinction ever of insects, which if you've ever tried to swat a fly, you'll know that it's almost impossible to wipe them out. They are really, really tough. The insects are incredibly durable as a group. So that tells you something about this extinction. If we're able to, or if the Earth is able to wipe out large numbers of insects, then this must be a pretty catastrophic event. If we have a look in the oceans, essentially everything in the oceans is affected. As many as 96% of species globally became extinct at this time. Some groups were completely wiped out. So things like the tabulate and rugose corals, they're completely wiped out during this event. Some things, the goniotites, for instance, devastated. There are 3 survivors that give rise to the rest of the ammonoids that we see later in the rock record. But pretty much everything is really, really devastated by this event. It's the end of the trilobites, so it's their final hurrah as well. So essentially, without going into the fossil record in too much detail, we can see that this is a devastating catastrophe for life on Earth. So, how quick was it? Because I said earlier, we need to understand whether things are fast or slow to try and understand what might have caused them. So if we go back to 2013, this was a paper that looked at foraminifera, so single-celled microfossils. These are range charts, so each one of these grey lines is an individual species, and that's their range through time. And the Permian Triassic boundary is there. So we can see that these things drop out in a kind of stepwise fashion, but we have a major latest Permian extinction at that level there. And then we have a second pulse of extinction in the earliest Triassic. And this paper used radiometric dating, so uranium-lead dating, to try and understand how much time was between those 2 pulses of extinction. And this paper summarised that there were 180,000 years between those 2 pulses, which is fairly geologically abrupt. There's since been more work done on this. So there's a paper that came out a year later, again looking at foraminifera, that argued for a much more abrupt extinction without actually putting a number on it. And then, same year, so 2014, so a little while ago now, but this is about the most recent radiometric dating that's been done on this, arguing that within the bounds of error bars, this extinction was actually much quicker even than those estimates, and suggested it was maybe only 60,000 years in duration. So geologically, that is very much an abrupt event. So we'll look at how nasty it got. So we've got the timing, we know what disappeared. What might have done this? So here is a paper, again, a good friend of mine, Yadong's son, did this while he was in Germany on a fellowship. He's now in Wuhan. And his work looked at conodont oxygen isotopes, which is a way of actually putting a number on sea surface temperatures. Clever geochemistry. So he was able to establish what was happening in terms of sea surface temperatures, and they were getting very hot in the tropics, up to 38, 40 degrees. That's the valve on your shower that controls how hot it is. Anything over 38 is pretty hot, as you'll know if you've taken a hot shower, but it's also beyond the reproductive capacity of most things that live in the sea. What we see there is that on land, the tetrapods move to the higher latitudes. They're clearly trying to escape the heat. In the oceans, these are ichthyosaurs and sharks. They also move out of the tropics. So clearly it's just getting very hot. Anything that can move, moves. Things that can't move, die. So clever piece of work, and it all fits very nicely, and leads to things like headlines like extreme global warming may have caused largest extinction ever. That warming is linked to increased carbon dioxide, much as we're seeing today. Hence headlines like this. The planet has seen sudden warming before, it wiped out almost everything. But there's quite a few other things going on. There is abundant evidence for substantial warming at this time. There's less evidence for ocean acidification, but it became a very trendy thing about 10 years ago in terms of the modern. So then people started trying to say, well, these past extinctions were also caused by ocean acidification. At the moment, there is not a single tool that allows us to really quantify what the pH of ancient oceans was. So boron isotopes are the leading kind of idea, but it's very difficult to do this. So these are generally inferred through indirect evidence, such as, do things with an aragonite skeleton suffer more high extinctions than something with a calcite skeleton, and so on like that. But it has been suggested that ocean acidification played a role in this extinction event. Ocean of acid blamed for Earth's great dying. Another thing that's around, there's a lot of mercury at the extinction level preserved in sediments. That also became very, very trendy in 2012. That was the first paper that really established this mercury spike at the Permian-Triassic boundary. Highly toxic metal. Could that have been responsible for extinctions as well? On land, we see ozone depletion in the atmosphere, and this has led to sort of ultraviolet B radiation and potentially vinegar-like rain, acid rain that had fallen during Earth's worst extinction. So lots of different ideas that are being suggested here. Apparently the rocks smell of vanilla, and vanillin is a compound that forms in soils when they're subjected to acid rain, which is really weird. Ice cream flavoured soils. And I mentioned UV radiation. So if you have a big hole in the ozone layer, ours is now nearly sealed, but not quite. You have ultraviolet B radiation, which causes things like malformations in pollens and spores, and then leads to extinctions in that way. I like bashing this particular group. These are based in Switzerland, and they're a bunch of annoying people, I will say. They just seem to publish stupid ideas for the sake of it. Things that go completely against everything else that we've sort of talked about. So this group wrote this paper, which I actually reviewed, and I said this is ridiculous because they're claiming that carbon dioxide is causing an ice age, which any scientist would know is stupid. They actually meant sulfur dioxide. So if you read it, you see that mistake is still in there, even though I pointed it out. They argue for a short-lived ice age, just to be provocative, and then admitted that there's no evidence for this ice age, and the ice age was so short-lived that it left no trace in the rock record. So supposedly reputable journals like Scientific Reports, they will publish anything if you pay them enough. Anyway, this is one of my papers, so this is obviously much better. This is, again, one of Yadong and Alex Farnsworth, who's a climate modeller at Bristol, published this last September, So this is our latest idea. Mega El Nino instigated the End Permian Mass Extinction. So El Nino, this is the most recent one, showing red spots that are oceans heating up. You probably know, but I'll say it anyway. Climate pattern in the equatorial Pacific, so it's the El Nino Southern Oscillation, or ENSO, to give it its full name. What that does is generates warmer than average sea surface temperatures. These disrupt the global weather, so we see increased rainfall in some areas, droughts in other areas, and temperature extremes, both hot and cold, worldwide. So basically, El Ninos destabilise weather, and if they're around for a long enough period, they destabilise climate. So this work was actually done, the modelling was done by Alex in Bristol, using the same model that the Met Office uses to forecast our weather and our future climates as well. It's a very complex model. I think it's called the HAD3CM model with some add-ons. Not my thing, but yeah, it's produced some quite interesting results. So what we have here is different carbon dioxide concentrations in the atmosphere. The model runs, so we've got pre-industrial carbon dioxide on the left there at 280 ppm, and then a range of estimates for the latest Permian, so 857 parts per million, going right up to 4,000 parts per million in the Indian. These estimates are not just wild numbers, these are based on various lines of evidence that have been published in the scientific literature. So the model tests what happens in terms of temperature anomaly in the sea surface temperatures at different carbon dioxide concentrations in the atmosphere. So you can see we have temperature anomalies once you get up to our predicted latest Permian concentrations of CO2 reaching round about 4 degrees C, which is not very much actually, 4 degrees C, but it's possibly enough to drive extinction, which we'll come back to later, because this is what we're seeing right now on Earth today. If you put in really, really high CO2 numbers, you don't actually see a much bigger increase in those temperature anomalies. So what we've shown with these models is that even relatively, well, I say low, this is still very high CO2 concentration, but it's definitely within the bounds of what we would expect for the latest Permian, can drive really significant temperature anomalies and longer, this is time along here in the model run, longer temperature anomalies. So, you know, thousands of years or hundreds of years rather than the modern El Ninos that tend to be years to a few years. This is what you would have in those same model runs if you had 5 consecutive El Ninos without much in the way of gaps between them. And what we see here, this is longitude, so we just did it from 180 east all the way around the world to 180 east. So this is Pangaea in the middle here. Temperature anomalies go really, really high. So if you multiply the effects of 5 of those El Ninos, which are on the previous slide, giving you that kind of 4-degree warming, here our scale of, in the tropics here is showing temperature anomalies perhaps of 10 degrees above average or above what you would expect. But intriguingly, that same anomaly is achieved even at relatively modest carbon dioxide concentrations. So CO2 is clearly, I mean, this is a model, and I said, you know, you could do anything with statistics, you could do anything with a model, but it's a good model, and these are reasonable outputs. So it shows that, you know, even under relatively modest, by Permian Triassic standard, CO2 concentrations, if you have enough El Ninos in a row, you can achieve the sorts of temperature increases in the ocean that would probably lead to extinction. So the conclusion of that paper was the Pangaean supercontinent was more susceptible to ever increasing El Nino events with increasing atmospheric carbon dioxide. El Nino increases the risk of extinction, enhancing low latitude warmth, and then this is a positive feedback. That creates stronger El Ninos. For terrestrial communities, prolonged extremes, droughts and high temperatures led to extinction, whereas the ocean suffered from heat stress and the expansion of anoxia, so the loss of oxygen, with equally disastrous consequences. So that's the conclusion of that paper, and I think it's, well, I helped write it, so I think it's right. What did it, though? What could drive all of this warming and El Nino and all the rest of it? These are the Siberian traps. This is a large igneous province in Siberia. It was one of the last to be discovered. So I've mentioned the Deccan traps you may have heard of, potentially driving the end Cretaceous extinction. This is almost certainly, in fact, this is accepted widely now in the scientific literature, that this is what caused the End Permian catastrophe. 6 million cubic kilometres of lava. There's Glasgow, big city, certainly bigger than where I live. That's enough lava. It's basalt now, but it's enough lava, it would cover the entire city of Glasgow in 34,286 kilometres of lava. So like, imagine a Glasgow-shaped lava pile, that tall, will go almost all the way around the Earth at its equator. So the circumference of the Earth at its equator is about 40,000 kilometres. So that's a Glasgow-shaped piece of lava that goes all the way around the Earth, almost. It's a shame it didn't. If Glasgow was just a little bit smaller, that would have been perfect. What does that volcanic eruption do? It releases carbon dioxide. So it's been estimated that the total carbon dioxide released by the Siberian traps was 30,000 gigatons, which, a very handy figure, is almost exactly 10 times the amount or the mass of CO2 in today's atmosphere. We'll come back to that. That's an outcrop map. Don't need to dwell on that. This is a map showing large igneous provinces globally. So there's lots of them, and some of these are associated with other mass extinctions, such as the Deccan traps, as I mentioned there in India. Some of them are not associated with any climate or ecological change at all, things like Ontong Java and Kerguelen, probably because they erupted into the deep oceans, so didn't do quite the same level of damage. But you can see up there, the Siberian traps, they're one of the biggest of these types of things, these large igneous provinces, hence capable of doing such significant damage. What about coal? So here's a George Monbiot article, how fossil fuel burning nearly wiped out life on Earth 250 million years ago. So the Siberian traps actually, they were discovered through coal exploration in Russia. It is a coal-filled basin as well. So that hot lava interacting with that coal probably generated additional CO2. And we see explosive eruption of coal and basalt at the End Permian Mass Extinction, catastrophic dispersion of coal fly ash into the ocean. So we do see lots of coal fly ash at the extinction level. So that does seem to hold up. Coal burning contributed to End Permian Mass Extinction. Now, next slide comes with a warning. I don't know if the speakers are on here and if it's loud or not, but there's a little video coming up. The speakers aren't on. I like testing things. So when those papers came out just over 10 years ago, I thought, I'm going to make some coal. I'm going to make some lava. This is the thermite reaction, burning at about 2,000 degrees. There's a piece of coal. This is a tray of sand. This is in our chemistry lab. I thought, can you set fire to coal with lava? And yes, of course you can. You can also set fire to the chemistry lab. And this is the coal fly ash, or the soot, and all the benches are covered in this fly ash as well. So, by my estimation, that's a reasonable explanation for an additional source of CO2 at the End Permian extinction event. Got into trouble for that, sadly. So this is our scenario. We have Siberian traps eruptions, does a whole load of things. The important things, this is in several of those published papers, so if you really want to go into this, download the 2017 summary. We get sulfur dioxide, we get halogens like chlorine and fluorine that can drive acid rain, as does sulfur dioxide. Toxic metals, they can directly poison things. The key one here is carbon dioxide emissions. These lead to global warming, as we know, which in turn leads to ocean anoxia, so deprivation of oxygen in the oceans. We have lots of feedbacks here. Our thermogenic gas, so this is our burning of coal, that additional gas, that could drive ocean acidification. It would also drive warming, then leading to ocean anoxia. On the acid rain side of things, we have acid rain and these halogens driving ozone depletion, increasing the UVB. So a complicated web of feedbacks and things. And this just neatly summarises what we know today about this extinction event. After the extinction, we have various gaps in the rock record. Coal gaps, so this is the end of Glossopteris, it's the end of coal for a long time. Reef gaps, reefs don't come back for about 10 million years, and various other gaps. One thing that I found weird is there are some odd survivors. This is Lystrosaurus. This is a nice graphic art card set by William Stout, who's an American artist, painted this in the 1960s. Is still alive, as far as I know, or was recently. It's a set called Lost Worlds. And this depicts Lystrosaurus, this reptile that survived the extinction, don't know why, looking out over a barren Antarctica. Most of the plants have gone and his friends have gone. And I like that because it just sort of makes me think how sad it is that we have these extinctions. But there is some positivity coming up. Like this. So we have this really long, arid, dry, hot Earth, very hot Earth. Not much there. Plants gone. You know, it's pretty barren and miserable. Then in the Carnian, in the middle Triassic, it suddenly, oh, is that late Triassic? I should know my Triassic timescale. Mid to late Triassic. About 20 million years later, it starts raining. And the Earth becomes green and lush again. And that provides the perfect habitat for Eoraptor, the first dinosaur, the earliest dinosaur, 21 million years after the End Permian extinction. So wiping out the planet, effectively wiping the planet clean, provides conditions for new life to evolve into, which we'll come back to in a little bit. Am I rambling? How long have we got? Oh no, we're fine. No one's got a bus to catch, have you? So this is the point here. New things always evolve into vacant niches, or niches. Once the habitat is, or the environment is habitable again, new things appear into it. But this can take millions of years. And then we've got Archaeopteryx, which evolved from the dinosaurs about 150 million years ago, following a period of environmental change that stimulates evolutionary adaptation. And if we go back to the end Cretaceous, it's only following the extinction of the dinosaurs, or the non-avian dinosaurs, 66 million years ago, that birds and mammals really take over the Earth. So the really philosophical thing here is, if that meteorite had missed Earth on that day 66 million years ago, would we even be here today? Probably not. So, you know, this is fascinating. We have to have extinctions to create space for evolution. So we'll get on to the modern now. A quick summary of what Permian life was hit by, and then we'll think about whether we should be worried today. So these are the multiple stresses that we know are associated. Maybe it's a combination of all of these or some of these associated with the End Permian mass extinction. We have thermal stress. So in the short term, volcanic eruptions, they produce sulfur dioxide. That can cause cooling because those sulfate aerosols can block out the sun. So if you think about the Laki eruption in the 1780s, there was a worldwide decline in temperature by about 1 degree caused by the Icelandic ash clouds. On a longer term scale, carbon dioxide drives warming that will completely override any cooling effect. Warming drives marine anoxia. Okay, so if you had a bottle of a fizzy drink or a nice pint of beer, which I'll hopefully have in the Brewdog pub next door later, cold, nice and fizzy. Bottle of Coke on the table in summer, cap off, the gas in there is going to evaporate out, or sorry, leak out, you'll end up with a flat drink. It's exactly the same with oceans. If they're warmer, gases leak out. Carbon dioxide goes in to some extent, which creates our ocean acidification, but in general, the gas will be lost out of a warmer ocean. It holds less oxygen, and therefore it can be prone to becoming anoxic and stagnant, which we're seeing in large parts of the world today. So I mentioned, you know, gases escaping from warmer liquids, but they will still absorb some CO2. And if we have more CO2 in the atmosphere, more of that CO2 is going to end up in the seawater. It then reacts to create carbonic acid, which drives ocean acidification, or pH fall, which is very bad if you're trying to make a skeleton out of calcite. We've seen ozone damage by halogens, increasing UVB radiation, which causes malformations in things like pollen and spores, amongst other things. Acid rain, possibly toxic metal poisoning. Darkness and photosynthetic shutdown has been invoked. I don't think it's the right answer in this case, but with the Chicxulub impact for the Cretaceous, it's been argued that, you know, you put up a big cloud of, in that case, basically shattered bits of carbonate that could block out the sun long enough to cause things that need the sun to photosynthesize to die out. Now, I don't think that's the case for this extinction. So here we go with the modern, and the last part of tonight's talk. Has Earth's sixth mass extinction already arrived? That was a question posed by Tony Barnowski in 2011 in the journal Nature, and this is a seminal figure. I mentioned Raupensatkowski's seminal figure from 1982 earlier. This is kind of the equivalent for the modern age. So what we've got here are different groups: mammals, birds, reptiles, amphibians, etc. on the left-hand side. Extinction magnitude, percentage of species in the past 500 years of each of those groups. And then these, up above around about 70-75%, are our big 5 mass extinctions. So you can see that some of these numbers are quite big. So on the left, we've got percent species extinct in the past 500 years. Overall, it's 0, but there are some groups that have suffered 1%. So the amphibians, for instance, have suffered 1% extinction of species in that time. Here we've got the numbers that include the International Union for the Conservation of Nature, IUCN for short, that have been assessed at being at risk of extinction. So this is the group that produces the red list and classifies things as endangered, critically endangered, vulnerable, and so on. So we see that these numbers are starting to get quite big, and in some cases more than 50% at risk. But as with everything, take that with a pinch of salt. So the gastropods, the IUCN thinks that 56% of them are at risk of extinction, but they've only assessed just under 3% of the total of gastropod species for their extinction risk. And that's because there are loads of gastropods. They're not very charismatic. The IUCN is much more interested in pandas and whales and things like that. So obviously they're going to assess their extinction risk before they get round to doing the gastropods. But it's quite scary because even despite that caveat, some of these numbers are getting towards 50-60%. So they're approaching the kinds of numbers associated with mass extinctions. Why? What's causing this? So this is the Keeling curve. This is carbon dioxide measured on a daily basis at the Mauna Loa Observatory in Hawaii, far away from any industrial sources of CO2. So it's thought to give the best representative overview of carbon dioxide in the world's atmospheres. And obviously it's been increasing steadily for many, many years. We're going to do some sums in a bit, simple sums, and we'll use the last 50 years for the basis of that. If we go back to 1975, 326 ppm CO2 in the atmosphere. Fast forward to today, it's about 420. It goes up and down due to the seasons, but on the whole, that's a 94 parts per million rise in 50 years. So we'll come back to that in a bit. Where does it come from? It comes from our, well, many sources, but by and large the biggest source is our primary energy consumption. And despite the transition in this country, the energy transition, we have the Eastern Green Link coming through my village, which is bringing electricity from Scottish offshore wind down to East Yorkshire. So that's a big thing at the moment, and clearly there's a big energy transition happening at the moment. But despite that, we can see that this is coal, this is oil, and this is gas in the grey, blue, and purple there. And this is the global energy consumption, and that's where it's coming from. And the expansion in the renewables at the top there, hydropower, wind, solar, biofuels, and things like that, it has expanded in that time. This is 1960 to the 2024 here. Those things are obviously expanded, but they're not keeping up with the overall global increase in energy demand. So we're putting out more and more fossil fuel derived CO2 into the atmosphere every year as a world population. What does that do? So here's a BBC screenshot from 5 years ago when it appeared that 2020 was set to be one of the 3 warmest years on record. And I remember this very clearly, thinking, oh, that's not very good. Well, if we go forward to 2024, the most recent year that we have a complete temperature record for, it's completely dwarfed the summer or the year of 2020 in terms of the warmth. 2024 was the warmest year on record. You can see here it's the first to breach that 1.5 above pre-industrial increase that was the basis of the Paris Climate Agreement. But that's 2020 there, which was one of the 3 hottest on record. 2020 there. We then had a couple of relatively cool years in 21 and 22, possibly because we all stopped flying in the pandemic. There was a significant decrease in CO2 emissions in 2020 and 21, or 2021, sorry, and 22. But the last 2 years that we have full data for have completely dwarfed those previous years. So they're the 2 warmest years on record by far. Some nice maps. This is one from NASA, and 2022 was actually one of the relatively cooler years of the past few years. Temperature anomalies. So if you think back to my Permian El Nino stuff, where we were looking at temperature anomalies of 5 successive El Ninos generating maybe 10 degrees of warming in some regions. Well, in 2022, there are plenty of bits of the world that saw temperatures in the sea surface 4 degrees warmer than the 1951 to 1980 average. 2024, the most recent year that I can find data for, the planet's basically, it's just heating up to extraordinary levels. So here we've got temperature anomalies of 6 degrees above the 1951 to 1980 average over vast areas of the world. There are a few tiny bits like up in Greenland where it's slightly cooler than average, but 99% of the world is way hotter than that 1951 to 80 average. And these are similar scale anomalies to those modelled by Sun et al. In that El Nino paper. We also see a decline in pH, quite an old figure now, but this is the estimated change in seawater pH created by CO2 between the 1700s and the 1990s from the World Ocean Atlas. And what we can see is this is a logarithmic scale, but we can see that particularly in the poles where the seas are cooler and therefore can absorb more CO2, these higher latitude regions are experiencing significant pH decline, which makes it hard to build a skeleton, as I say, if you're using calcite. Another way of showing that, this is aragonite saturation state. So aragonite's just another form of calcium carbonate, very closely related to calcite. Chemists amongst you will know that. Many things build their shells. It's actually the favoured precipitate to make your shell out of if you're a carbonate shell builder. So many corals and things like that use aragonite to build their shell. If the saturation state is below 1, which it's predicted to be, this is a prediction of the year 2100, you will dissolve. Okay? So it's corrosive. So these are corrosive oceans, particularly in the higher latitudes, but also in the sort of mid latitudes as well, becoming corrosive. If you can't build a shell, you can't exist. So this is a real problem for the world's carbonate ecosystems. So that's all quite worrying. Are we indeed doomed? How close are we to a Permian-style catastrophe? So this is where the numbers come in, and it gets a bit silly, if it wasn't silly enough already. Mentioned earlier that the total mass of CO2 in the atmosphere was about, give or take, 3,000 gigatons. And the Siberian traps released 30,000 gigatons. So that's a nice easy sum. 3,000 or 30,000 over 3,000 is 10. So the Siberian traps were releasing 10 times the CO2 in the modern atmosphere. A helpful round number. This was enough to wipe out 96% of species. I showed you earlier the Keeling curve, and in the past 50 years, CO2 in the atmosphere has increased by 94 parts per million, or 1.8 part per million per year. So how long would it take at present rates of carbon dioxide increase in the atmosphere to multiply our present atmosphere by 10? So take it to 4,200 parts per million. So we'd need to add that much, because if we're looking at getting towards 4,200, we take away the current 420 in the atmosphere. So we'd be looking at an increase of 3,780. Which at 1.88 parts per million per year would take 2,010 years, which is not very long. I think you'll agree that is geologically instantaneous. So we could have a Permian-style catastrophe striking by the year 4035. I'm not going to put a bet on that, but, you know, these numbers, these are very, very, very short timescales. Even worse, if we consider that anthropogenic CO2 emissions, they've gone up and up and up. They're now, or last year globally, 43 gigatons of CO2 were emitted to the atmosphere by humans. So to get 30,000 into our atmosphere, it would take only 698 years to release the same mass of CO2 as the entire Siberian traps released in the Permian. So that gives us an extinction day as soon as 2723, so really soon. So if you think about that and what's happening at the moment, you might think that Earth is surprisingly close to a major mass extinction state, and that Tony Barnowski's right, the sixth mass extinction has already arrived. But who thinks that's going to happen? Hands up. A few. Who thinks it's definitely not going to happen? Who doesn't know? This is our detailed sustainable energy transition path, which sounds ace. This is the phasing out of fossil fuels for our energy demand over the next 20, 30, 40, 50 years. And by 2100, there will be almost no, in fact, even sooner than that, the transition path suggests that we will be burning almost no fossil fuels, so therefore emitting no CO2 for our energy demand. Of course, there are other sources, cement manufacture, things like that, are highly carbon dioxide rich processes. But if this happens, that net 43 gigatons per year to the atmosphere should significantly reduce. In fact, I haven't got a slide on this. I showed it to students the other day. The UK obviously had a plan to reduce the UK's carbon footprint significantly to net zero by, was it 2035? I can't remember. The government's latest figures for the UK as a whole say that the UK has reduced its carbon emissions by 68% already since that target was set. Now, that's a bit of a fiddle because it's been done by moving manufacturing to other parts of the world, so that CO2 is still being produced. If you look at the overall figures for our CO2 footprint, including export, import, and the whole carbon footprint of the whole supply chain of the things we have, that 68% reduction falls significantly to about 30%. But it's still good, it's still progress. But it is a bit of a fiddle, and that's, I guess, what governments are there for. Another thing, though, as geologists, we can probably take a bit of solace, not in government figures, but going back to this figure, if you think about it, that's the time of Pangaea. Nothing much has happened in terms of extinction since the time of Pangaea. Pangaea breaks up throughout the Triassic and into the Jurassic, and now we have the world as we know it today, very different geographically nowadays. And there's only been one extinction since Pangaea broke up, and that's associated with that impact of the meteorite in Mexico, as well as the Deccan traps, potentially. But since then, Earth's been fairly stable in terms of life on Earth. So perhaps not having a supercontinent is also good for life on Earth. Penultimate slide, a little aside. Anyone know what these are? Coccolithophores, yep. Or coccoliths for short. A lovely scanning electron microscope image. Calcareous nanoplankton. Very boring subject, but very important things. These appear in the Triassic and really get going in the Jurassic. So these evolve into some of the empty ecospace in the oceans. There were no calcareous nanoplankton before the End Permian extinction. Maybe Earth evolved these to sort out our carbon cycle. So what these do, if we go to where I live, we have fantastic white chalk cliffs at Flamborough. You've maybe been there. Better than the chalk cliffs on the south coast of England by far. They're built of trillions and trillions of these things. And what happens when these die? They build their skeletons out of calcium carbonate, which sucks CO2 out of the atmosphere, sink to the seafloor in their countless numbers. Over time, they form rock as they're compacted and buried and lithified. They form chalk. That chalk is a permanent geological store for the CO2 that these things sucked out of the atmosphere when they were alive to build their shells or tests. So the evolution of these things is completely fundamental to the carbon cycle. Now, if these things start to disappear, because they can no longer build their skeletons, because the saturation state of the ocean is so bad that it's become corrosive, then I think we probably would have that kind of runaway carbon cycle warming effect. So we really need to take care of our calcareous nanoplankton in the ocean. Now, I don't think they're under significant threat at the moment. I'm not an expert on these, but we should definitely be grateful for these things in regulating our carbon cycle. And with that, I will finish with a silly cartoon, which has a spacecraft flying away saying, "Idiots, that's the UN report on global warming." So there we go. I'll finish there.